Okay.
Okay, so we are delighted to have Seshadhri for today's talk. So, in Sesh's own words, there's some confusion about his name, and we'll use this proverb to add to the confusion. Uh, he has been referred to as C Seshadhri, Commando S. So there's some confusion, but since he recommends his friends to call him Sesh, we'll go with that. Before we go further, let's go around the table and introduce the groups. So we have Akash Kumar from Purdue. Hi, Akash. Um, then we have Clement Canon from Stanford joining us. Hi, Clement. They are muted. Then we have Irfan. Irfan is joining us from Indiana University. Hi, Irfan. Okay. Then we have Gautam Kamath from Simons. Then we have Dead Vakev, who is also one of the organizers. Sam Holmes. I am sorry, I do not know where you're joining us from. We can't see you. Then we have Shravas Rao joining us from NYU. We again can't see you. Toma Vidik leading the group from Caltech. Hi, Toma. And then Shin joining us from Toronto, and Yijun joining us from Michigan. So before I go further, let me just thank all the other organizers, Oded Regev, who is Oded Regev, Gautam Kamath, Clement Canon, Ilya Rajinstein, and Thomas Vudik. And the next to talk, the next talk in a couple of weeks is by Mihal Kutsky, and 2 weeks from then is Urmila Mahadev. So we have an exciting lineup of talks lined up. And as usual, you'll be muted during the talk. But if you have a question, unmute yourself. And before we go further, today's speaker is Seshadhri, who is a faculty at UC Santa Cruz. Before this, he was on the at Sandia National Labs. He did his PhD from Princeton, and he did his undergrad from IIT Kanpur. So Sesh and I went to the same school. And Sesh has worked in a variety of areas, including sublinear time algorithms and data mining. And today he's going to tell us about finding forbidden minors in sublinear time.
Okay, should I start?
Yes.
Okay. All right. So thanks a lot to the organizers for the invitation and for organizing and setting everything up. Thanks, Ananya, for the introduction. So without further ado, we'll begin. So the talk is finding forbidden minors through random walks, almost square root n query one-sided testers for minor closed properties. Sorry, that's a bit of a mouthful. This is joint work with Akash Kumar from Purdue, who's joining us, and my student Andrew Stolman at UC Santa Cruz. And this it just appeared at Fox 2018. Okay, so let's start with an old classic fact that probably most of us are familiar with, is this theorem of Kuratowski, or technically theorem of Wagner, which says that G is not planar if and only if it contains a K5 or a K33 minor. So just to explain, so here is the K5, here is a K33, and here's a planar graph, a graph that can be drawn in the plane. And what this theorem says is, if the graph cannot be drawn in the plane without crossings, which is sort of a geometric fact, then there's actually a topological restriction, means that it must contain a subgraph that's a kind of copy of K5 or K33. And that's a minor, which I'll explain shortly. So it's sort of from geometry to topology. It says this geometric fact of being planar or being not planar can be expressed through a topological restriction. Specifically, what is a minor? So if you start with the graph G, a minor is obtained by three processes. So either you delete vertices or edges, so that's just getting a subgraph, and then you have a contraction step. So you can delete vertices, delete edges, and contract edges. So you take this edge, you contract it to get the sort of super vertex. And H is a minor of G if it can be obtained by these operations from G. Maybe a better pictorial view is a K33 minor is effectively something like this. Instead of each vertex of K33, you replace it by a vertex disjoint connected subgraph. And instead of every edge, you replace it by vertex disjoint paths. And this subgraph is a minor. So, or rather, if G contains such a subgraph, then it contains a K33 minor. And if you think about what Wagner's theorem, Kuratowski is slightly stronger, but it basically says that G is planar if and only if it does not contain K5 minors and K33 minors. So this is referred to as a forbidden minor characterization, meaning that a graph has a property if and only if it doesn't contain some list of finite minors. And another common forbidden minor characterization, simple one, is that if G is a forest, if and only if it doesn't have a K3 minor. So, Wagner's theorem was the first that came up with this forbidden minor characterization. And of course, there is this deep series of results by Robertson and Seymour, arguably one of the most profound results in graph theory, which says, if you have a property P, such as planarity, that is closed on taking minors, meaning that if you apply any of these operations, vertex deletion, edge deletion, or contraction, then the resulting graph still has the property, then P has a finite forbidden minor characterization, meaning that for any such property, a graph does not have the property if and only if it contains one, of a list of finite minors. So if you look at properties like planarity, outer planarity, being bounded genus embeddable, having tree with less than k for some constant k, then each of these properties is minor closed, and therefore actually has a finite list of forbidden minors. So this was, this was sort of an incredible result that generalized Wagner's theorem for planarity. And from an algorithmic perspective, you can ask, suppose I'm given a non-planar graph G, then can I find a forbidden minor in it as a certificate of non-planarity? And indeed, the classic result of Hopcroft and Tarjan in the 70s gives a linear time algorithm to decide planarity, and it actually produces such a restriction or such a minor in a non-planar graph. And again, the whole body of work by Robertson Seymour also gave algorithms. So again, I'm going to think of H as having constant size, so some fixed constant. So there is actually a cubic time algorithm that, given any constant H, can decide if G contains an H minor. So for example, if I take this wheel graph and I want to ask, does G contain this graph as a minor? That is equivalent to asking, does it contain a subgraph of this form where each vertex here is replaced by a disjoint connected subgraph and each edge is replaced by a disjoint vertex disjoint path. So this remarkable theorem, like algorithm with the previous theorem of Robertson Seymour, says there's a cubic time algorithm to decide any minor closed property. And Kawarabayashi, Kobayashi, and Reed have given a quadratic time algorithm. So one can look at this as a grand generalization of Hopcroft-Tarjan with, of course, a worst running time, a quadratic running time, but polynomial nonetheless. And so what motivated our work is, suppose you can't read all of G. Then what can you do? Are there little O of n algorithms for minor finding, and specifically in the context of planarity, are there little O of n algorithms for deciding some version of planarity? So let me explain what I mean by sublinear time. I have to explain what is the query model of the graph. So we'll think of bounded degree graphs. So think of a bounded degree graph stored as an adjacency list. There are n vertices, and there's a degree bound of d. So n and d are the parameters of interest. That gives you the size of the graph. We have two kinds of queries. The first is a vertex query. So basically, you roll dice and you get a uniform random vertex in G. So that's one query. And the second query is a neighbor query. So given any vertex V, or in this case, I've shown W, and given any I index less than the degree bound D, you can get the ith neighbor of that vertex. And if the degree is actually less than I, then it just returns null. So it's some simple way to give you query access to the adjacency list. So just to recap the model, there are basically two kinds of queries. There's a vertex query where you can get a vertex uniformly at random. And a neighbor query says, for any vertex, you can essentially get a neighbor. You can get the ith neighbor. And but sort of algorithmically, I think it's easier to think about, basically there are two operations. You can pick random vertices, uniform random starting vertices or seeds, and you can crawl from these seeds by doing those neighbor queries. So effectively, you can do something like a BFS, or you can do some kind of random walks. So you can think of this query model as capturing the algorithmic power of these operations. Now, if we want sublinear algorithms for planarity, we have to be a little careful, because obviously you could have a planar graph with one K5 minor sticking over here. And of course, this whole graph is not planar, but there's no way that a sublinear time algorithm could find this. So you have to have a more sort of nuanced notion of what it means to be not planar. And so what we'll do is, as in property testing, we define that G is epsilon far from planar if at least epsilon ND. So ND is the the total number of edges, or it's an upper bound on the number of edges. So we'll say G is far from planar if at least epsilon ND edges need to be removed to make it planar. So a graph G is far from planar if you remove an arbitrary set of epsilon ND edges and it's still not planar. And so this is some sort of measure of how far it is from being planar. And naturally, one can define such a notion for any H minor freeness or any minor closed property, or actually any property in general. And because all of these properties are sort of closed under taking subgraphs, we'll say G is epsilon far from being H minor free if at least epsilon ND edges have to be removed to make it H minor free. So this is the notion of distance that we have. Now, with this sort of introduction, I can give you the main result. The main result is, so fix some H, constant size, and fix some epsilon. There is a root n time algorithm. So ignore the O star for now. There is a root n time algorithm that if G is epsilon far from being H minor free, then the algorithm actually finds an H minor in G. And there is a linear dependence on the degree bound D. Now, in the context of bounded degree graphs, we generally think of D as a constant, but I think it's nice that we can just sort of explicitly put the dependence on D in this expression. The O star I will use to sort of hide polynomial and 1 over epsilon factors in the sort of the distance parameter, and it's also hiding some sort of n to the little o of 1 parameter, which is a bit of a detail. It's naturally a randomized algorithm. It has a success probability of 2/3. And there are older results of Goldreich and Ron and actually Chuma et al. That show that there is a root n lower bound for this problem, and therefore the exponent of half is actually optimal. So this algorithm, up to some dependencies in the O star and the D is optimal. And this is a sublinear time algorithm to find minors in graphs. So maybe at this point I'll pause, and if any of you have any questions on the result, I can take any questions.
Maybe just for some context, how does it compare with like finding triangles? It's a different question, right?
It's a very different question, because essentially a triangle is if you think about a minor is actually a very large subgraph when you blow it up, whereas a triangle only has 3 vertices. So even though you're looking for, let's say, a K5 minor, it could have many vertices in it. Okay, so I'll continue now. And I think maybe one of the most important corollaries of this result is if you fix a minor closed property P, so by Robertson and Seymour, there is a finite list of forbidden minors, then there is basically an O star of root n time algorithm such that if G is epsilon far from having the property, then the algorithm produces a forbidden minor, in sort of randomized time. There was a question that popped up, and if I see it again, I could answer.
So Clement asks, does that mean this improves on the n squared state of the art, even for d equals n?
So that's a good question. So the answer is no. I'll come back to this at the end of the talk. I'll come back to that question. But the answer is no, because it's only if G is epsilon far from being planar, and the dependence on epsilon is like some large polynomial. So you don't get any improvements. And you'll see that it actually uses the exact minor time finding as part of it. So I'll come back to this question at the end. What this says is, if you fix a minor closed property, if G is epsilon far from having the property, then there's an algorithm that produces a forbidden minor in G in root n time. And so now this property could be planarity, outer planarity, series parallel, any minor closed property. And no sublinear algorithm was known for this problem, even for the special case of planarity. And planarity was considered the major challenge. And what is interesting is, when we got the algorithm for planarity, we could generalize it for all minors. Let me also give you a very cute corollary of the corollary. So take a d-bounded degree, meaning that a graph with whose maximum degree is d, with at least 3 plus epsilon n edges. Now, such a graph is automatically epsilon far from being planar, because a planar graph has at most 3n edges. Then, for such a graph, there is actually a root n time algorithm that finds a k5 or k33 minor. And there is an analogous theorem for any minor closed property where you would replace the 3 with the appropriate degree bound. So, so this is sort of an it's sort of an unconditional statement. There's no assumption about distance because that's sort of embedded into the number of edges. Although it does work only, there is this dependence on the degree bound, the maximum degree. Now, I've sort of phrased this result purely sort of algorithmically, and let me now give you the property testing context for where this came up. And the property testing perspective is the way to think about this is the universe of all graphs. This blue portion here is, let's say, all planar graphs. And the yellow portion is all the graphs that are far from being planar. And in the middle, you have sort of this no man's land where essentially a property tester is allowed to answer whatever it wants. Now, property tester basically says if you have a graph in P, you have to accept with probability 2/3. If it's far from P, so it's here, you have to reject with probability 2/3. And the aim is to get typically either O of 1 or little o of an algorithms, depending on the problem. And one-sided testing says that if G is in P, then you have to accept with probability 1, which in effect says that whenever the algorithm rejects, it provides a certificate of rejection. Now, in the context of in planarity, it makes a lot of sense because let's say the algorithm, the tester, explores some small portion of the graph. If it rejects, then basically this subgraph that has been observed must contain the forbidden minor. So it's actually giving you a certificate that the graph is not planar. So in the context of planarity, one-sided testing is interesting because we actually get a forbidden minor. The tester must be giving a forbidden minor as part of just the vertices that it explores. Just to give you a little bit more context on where this result lies in the world of property testing basically has the two worlds of dense graphs and sparse graphs. And essentially, the world of dense graphs is relatively well understood. So in a dense graph, you're doing property testing with graphs with at least n square edges. The algorithms are typically independent of n. They're typically very generic. There's just you sample a random set, you look at the induced subgraph. And if you ignore the dependencies on epsilon, it's fairly well understood. On the other hand, the theory on sparse graphs is not as well understood and is much more algorithmically interesting. So this is the model that I gave you earlier of Goldreich and Rahn on how you can sort of crawl in a graph. Initially, connectivity properties were studied, and it was not clear until about 2005 or 2006 whether there actually was a large body of properties which were testable. And then there was a seminal work of Benjamin, Schramm, and Shapira, which I'll explain shortly, which says that two-sided testing is intimately related to something called hyperfiniteness. Now, a lot of this verbiage is not important, but the main takeaway is that one-sided testing versus two-sided testing seem to be very different in the sparse graph world, whereas in the dense graph world, they both happen to be roughly the same. And the algorithmics in the sparse graph world are much more interesting, the sublinear time algorithms or the property testers. So let me tell you about the result of Benjamin, Schramm, and Shapira. So it's the bounded degree graph model, as we just discussed. And they prove that every minor closed property is two-sided testable in triply exponential and 1 over epsilon queries. And it's an open problem to improve that to polynomial in 1 over epsilon. But contrast this with a one-sided lower bound. So what this says is if you want to do property testing of planarity, and you are allowed to make mistakes on planar graphs, then you can get something that's essentially dependent only on the proximity parameter. But if you actually want a certificate of rejection, meaning that you do not want the algorithm, the tester, to error on planar graphs, then there is a root n lower bound. So there is this interesting gap, this huge gap between the one-sided and two-sided case. And indeed, I know this is sort of a snippet from their paper. They conjectured that for every h, being H minor free can actually be tested with one-sided error in root n query complexity. And we essentially resolve this conjecture up to n to the little o of 1 factors. And so we prove that a large class of natural properties, which are all the minor free properties or the minor closed properties, are one-sided testable with square root n queries. And previously what was known was a result of Chumai, Goldreich, Rahn, myself, Shapira, and Solar showed that you could solve this problem with root n time when H is a cycle. So just to go back a second, you want to test whether it's being H minor free. And if you do K3 minor free, that's basically the property of being a forest. And if you do something like C5 minor free, you're just seeing like it doesn't contain cycles of length, let's say 5. So this was solved for H being a cycle in root n, in root n time. And it was done through a reduction to the bipartiteness tester, which I'll come to shortly. And recently, Fichtenberger, Levy, Vasudev, and Watzel gave an n to the 2/3 algorithm if H is K2R. Now, ignoring the sort of the various H that was being considered, effectively all of these algorithms argue about finding multiple paths between the same two vertices. Because if you find two different paths between two different vertices, then you get a cycle. And so it's all about, I'm going to start at a vertex and try to find two paths or maybe K paths to another vertex. And these techniques didn't seem to generalize for something like planarity, where you're now trying to find a K5 minor, because you have many vertices and you have to link them all to each other. And many of the techniques would start breaking down. At this point, I'll also pause, because now I'll sort of get into the actual details of the result. So if you have any question about the result, now is a good time to ask. All right, I'll continue then. So instead of giving you the nitty-gritties of the proof, which is actually fairly complicated and the algorithmics are quite intricate, let me actually tell you the story of how we got to the proof and really about all the missteps along the way that you may not see in the paper. So in the context of planarity, let's just talk about K5 minors. So let's say you want to find K5 minors in a graph that is far from being K5 minor free. So, sorry, let me just close that. Okay. So interestingly, our result has no Robertson-Seymour machinery. There are no brambles, there's no tree width. The sort of the standard toolkit of graph minors doesn't appear pretty much anywhere in our result. In searching for the H minor, it turns out H actually does not play a very significant role in sort of the main technical contribution. It's actually much more on spectral graph theory and how you can find minors through random walks, or what do random walks in graphs that are far from planar behave like. So let me start with actually, if you wanted to, embark on this result, and people have thought about this question, the starting point is actually a result of Goldreich and Rahn in '99 on testing bipartiteness. So this is sort of the seminal result, which I think contains the kernel of the ideas for our result. So you want to test bipartiteness for bounded degree graphs. So again, it's in the setting where n vertices, the maximum degree is d. And Goldreich and Rahn gave this remarkable algorithm that said if G is epsilon far from being bipartite, there is a square root n time algorithm that finds an odd cycle. So what does it mean to be epsilon far from bipartite? It means you take any bipartition, and for any bipartition, there are at least these epsilon dn red edges that are sort of on the same side of the cut. And this was the main inspiration for a result on how you can find cycles through random walks, which is what they do. So let me explain how Goldreich-Rahn actually work, and then let's try to sort of follow that template for K5. So they say, first, let's assume G is an expander. So this graph that is far from being bipartite is an expander. And so the mixing time, which I'll denote by L, is log n. So here was the idea. Say pick a random starting vertex here. So this graph is the same as this graph. I'm just showing the random walks here. So you pick a random vertex, starting vertex S, perform square root n L length random walks. Right? So you perform square root n walks of length L. Now these walks are mixing. So the end point of the walk is basically uniformly distributed, which means if you apply a simple birthday paradox argument, because of the root n, you are guaranteed that two walks are going to end up at the same vertex. So this could potentially give you an odd cycle. And the interesting part of their analysis is to show, okay, so that part is sort of hidden, or maybe
click on
not.
the hide button. Just click on
Yeah,
the hide.
I can hide that there. The interesting part of their analysis is to show that because G is far from being bipartite, if you look at a path from S to V, it basically has at least epsilon probability, conditioned on the path going from S to V, at least epsilon probability of either having odd parity or even parity, where parity is, the parity of the actual path that is generated. So conditioned on two walks actually hitting the same vertex, which is a high probability event, one of them is likely to be even and the other is likely to be odd, with like some polyepsilon property, and that gives you the odd cycle. Now, so this is, the rapid mixing case. And what we can do is now try to do solve the rapid mixing case for K5. So instead of the graph being a minor, an expander, let me think of it being a disjoint collection of expanders. So again, the mixing time within each piece is log n, and all these pieces are disjoint. And I don't care about the size of these pieces. Let me pick a random starting vertex S. Now I have to be a little careful because I want to have 5 seed vertices to connect. And those 5 seed vertices must come from the same component. So I pick a random starting vertex S and I perform 5 L-length RWs. RWs is random walks in my slides. So I'm going to perform 5 L-length random walks to reach these 5 vertices V1 to V5 denoted in blue. So I start from S, I pick 5 L-length random walks. These are uniformly distributed. And now we will try to connect V1 through V5 by random walks to form a K5 minor. So that's the plan. So you have these 5 vertices in some component. Now, if you think about it, the analysis will just go through that you can perform root n L-length walks from each vertex. And by birthday paradox, you are guaranteed to connect all VI VJ pairs, that with some union bound. So it's not hard to show that you can connect all of these 5 vertices together. Unfortunately, those paths are not going to be internally vertex disjoint. They will intersect each other quite heavily. So it doesn't necessarily imply that you'll get a minor. To get a minor, you need to be in this good situation where actually you can draw some kind of radius around each of the seeds and ensure the intersections are contained within. So here the intersections are contained within here, and similarly within, so that the portions outside these bubbles are all vertex disjoint. This will give you a minor. Now, in the bad case, you would not be able to find such a decomposition. Another way of saying this is the intersections have to be sort of benign. You need to be able to contract away the intersections to actually get a K5 minor. And so just connecting the paths is not enough, but you need to show the minor. Now, it turns out this isn't particularly hard because if you think about it, let's look at this component. We generated these 5 vertices independent of each other, and they're essentially uniformly distributed. So if you look at any VI and VJ, you look at the path that is formed between them by doing random walks from VI and VJ, this whole structure is independent of a VK that has been picked, right? Because VK is picked through an independent random walk. So another way of saying this is effectively short walks from VK are unlikely to hit this path because essentially all of these things are, you found a path over here, then you pick a uniform random vertex in the entire graph or in the entire expander component. And there's some union bounding that has to be done, but it's all feasible. And so you can show that this algorithm finds a K5 minor or indeed any KR minor in an expander. And so it's an alternate proof that expanders contain large minors. And echoes of this argument were there in a result of Kleinberg and Rubenfeld about more than 10 years ago on how to route in expanders. All right, so where does that leave us? It says that if you are in the rapid mixing case, meaning that the graph is a disjoint collection of expanders, then it turns out that it is automatically far from being planar because expanders are not planar. And there is a square root n time algorithm to find a K5 minor, and it's done as follows. You pick a uniform random vertex, starting vertex S, that is denoted in black. Then you perform L-length random walks to get 5 starting vertices, V1 to V5. From each of V1 to V5, you perform square root n L-length random walks, and that will give you the log n sized That will give you the minor, and the minor actually has size log n, and root n is optimal for this problem. So this is really where the root n comes from, and this analysis is not too hard to do. So I'll pause here if there are any questions. Okay, I will continue. So now, for the real meat, and I mean, well, I shouldn't say meat, I'm vegetarian. So I'll say masala, which is sort of an Indian term for spice. So now, now this is where stuff really gets interesting. How about you just run this algorithm on any graph and see what it does, right? So we use the expander case to come up with the algorithm, but let's just analyze this algorithm on any graph. So this is exactly sort of the deep insight of Goldreich-Rahn, where they said, and now in hindsight, when you look back, you're basically, that every graph can be decomposed into expander-like pieces. So you can remove epsilon dn edges and get disjoint pieces whose mixing time is essentially polylog n. And this is not too hard to prove. Trevisan proved this in 2005. But deeper results of this form have echoes in algorithms for the unique games, like the Aurora-Barak-Steurer result on sub-exponential time algorithms for unique games, essentially proves results of this form with stronger parameters, which is not required for this case. But the problem is there's a sublinear constraint. So we know that G can be decomposed into G prime, which is disjoint collection of expander-like pieces. And you could say, okay, so you can now run the algorithm on G prime, but a little O of n time algorithm doesn't know the decomposition. It can only perform random walks on the whole graph and hopefully simulate the algorithm on each piece. Now, this is basically a huge can of worms, because random walks will obviously leave the decomposition and come back. So because the total size of this cut is epsilon nd, random walks are going to leave and come back. And so it's pretty hard to argue that you can simulate the algorithm on each piece by an algorithm that is doing random walks on the whole, like something that is oblivious to the partition. So the main sort of technical piece of Goldreich 99 of the GR99 bipartiteness result is a particular decomposition result. Now, I'm going to state this in a way that is technically incorrect, and there are some parts of it that seem absurd because the actual description is quite involved. So let me state it in this way, and if you have complaints, then you can stop me. So I'm going to say for any graph, there's some k, so that if you pick S1 to Sk uniformly at random, so these are seed vertices, then you can actually remove epsilon dn edges. So you remove these, and you get these pieces P1 to Pk, such that Si is contained in each Pi, and length L random walks. So remember, L was like the mixing time. It was like some polylog n. In G from Si, reach all vertices in Pi with roughly the same probability. And that probability is something like 1 over square root n. So essentially, it's some very small probability. So these pieces could be very big. But on the other hand, you know that random walks in G, so you're performing random walks in the original graph, but it essentially reaches all the vertices in each Pi with roughly the same probability. And the seed vertices, essentially, there's a lot of flexibility in picking the seed vertices. That's what I mean by you pick them uniformly at random. So this is a slight, I'm mucking with their statement, but this is the essence of their statement. What is important to note is you're doing random walks in the original graph and are able to say something with respect to some decomposition that the algorithm does not actually know. And so L random walks, that's L length random walks in Si, from Si in G, reach all vertices in Pi with roughly the same probability. And now if you apply the expander analysis for bipartiteness, things go through. And essentially, if G is far from being bipartite, then a constant fraction of PIs are far from being bipartite. So there's a question.
Yeah, there's a question from Clement that how does the decomposition on this expander-like pieces compare to regularity lemmas?
You can maybe, I guess the Aurora-Barak-Steurer decomposition, which is also let's say, a different variant of this, is interpreted as a regularity lemma, although in the regularity lemma, it's more about what does the cut look like. And here, it's more about what the pieces look like. So there's really a difference between that. How many vertices do the pieces have? You have no control. So for example, if the entire graph was an expander, then the whole thing, the whole graph is one piece. And so it really depends on what the structure of the graph. So it's merely just saying the existence of this, and the important thing being that random walks in the original can actually tell you something about this decomposition. But note that the algorithm does not try to find the decomposition. The sublinear time algorithm just runs the expander algorithm, and the analysis shows that it can be simulated on this decomposition. Okay. So how can so many vertices have a probability of 1 over square root n? I said, so sorry, did I? No, sorry. I'm sorry. My apologies. This is a typo. So what I meant is actually this should be at most. It should be at most. So in their analysis, all the probabilities are at most 1 over square root n. Sorry, that was a typo. Okay, I will continue. So now that you have this decomposition, you could say, well, let's now try to generalize the algorithm for planarity in the same scheme. And there are two real major problems for minor finding. And this is when you realize that finding cycles is so much easier than finding minors. So remember that it says L random walks from SI reach all vertices in PI with roughly the same probability. Now, for finding a minor, remember, if you look at any piece, you need to do random walks from 5 different vertices to get a K5 minor, because that's how you link them up together. This guarantee in this result is only from one vertex in PI, which is enough for finding a cycle, because from one vertex, you just need to have 2 walks that that collide. But it seems like you'd have to generalize this to be able to get this property over here for many vertices. And that seemed very hard. So we struggled with this for quite some time, which is how can you get this property for multiple vertices? And so this is problem number 1 when you go from cycles to minors. There's an even bigger problem, which is in some sense coupled with this, which is if you look at L random walks from SI, they reach all vertices in PI with roughly the same probability. But these walks can leave PI, and we have no control on what they do outside. And so for an odd cycle, this is okay, because even if they intersect heavily outside, as long as the parities of the walks are different, that's an odd cycle. But for minors, this completely, it completely destroys all the structure. And the natural thing at this point was to try to strengthen the decomposition to get some handle on 2 things: getting multiple vertices in each piece to have a good behavior, and to try to control what happens when the walks go outside. And we were stuck here for a while. There's a fundamental problem, which is that you need to walk at least log n steps to do anything, right? Because the whole graph may be an expander. But there could be epsilon n cut edges. So the walks are going to leave the piece with high probability. So, initially we were trying to find decompositions where maybe the walks leave the piece with low probability, or you try to control how often they leave. But, that seems hopeless, because no matter what you do, the walks will leave with high enough probability from most vertices. And so we were stuck for a long time trying to improve the decomposition or tighten the decomposition. And we were here for, more than a year. And because the natural thing seemed to be, we've solved the expander case, let's now improve the decomposition so that we can just run the expander algorithm. And after being stuck here for quite some time, sort of went back to the drawing board and we said, let's revisit the expander case and maybe ask ourselves, when can random walks find minors? Maybe we can actually generalize the expander analysis to a much more general set of graphs. And that's where sort of one of the main insights of our work comes in. And I'm going to define something called leaking random walks, or leaky vertices. So I'm going to set L, the length, to be n to the delta. So don't worry about what delta is. Just think of it as more than polylog n, right? But it's small. Now let PSL be the probability vector of an L length random walk from S, right? So you start from S and you take an L length random walk. And let this yellow part be sort of the set of vertices that are reached with some reasonable probability. Or maybe this is, in some sense, roughly speaking, the support of the distribution. I'm going to call S leaky if the 2 norm of this probability vector is at most L to the minus 10. Now, another way of thinking of this is you take an L step walk from a vertex, and you can reliably reach at least L to the 10 different vertices. So clearly, expanders, all vertices are leaky because a random walk will reach everything. And here I'm just asking that an L-length walk reach something polynomial in L. Okay, is this definition clear? So this is what a leaky vertex is. The beating heart of the paper, one of the main results says if there are at least n over L leaky vertices, which is quite small because L is something like n to the delta, then the random walk algorithm finds a K5 minor with high probability. Like just the algorithm I described with some minor parameter tweaking will find a minor. And if you want a KR minor, you have to change the definition of leaky, the polynomial in the leaky. Instead of L to the 10, you have some dependence on R. And a corollary, of course, is a planar graph has at most n over L leaky vertices. I don't know if this is known. It may be derivable from some of the spectral bounds on on planar graphs. But yeah, I'm not sure if this is actually known for any general minor free graph. And note that it is curious that a planar graph can have leaky vertices. So if you take a balanced binary tree, the top few levels are actually quite leaky. Right? Because if you pick a vertex here and you do a random walk, you will reach the entire subtree. So a planar graph has at most n over L leaky vertices, and it actually does contain some leaky vertices, which in some sense means this corollary is a little harder to prove. And so, sorry, just to go back. So we said if there are n over L leaky vertices, the random walk algorithm finds a minor with high probability. And what about the other case? Now, in the other case, suppose there are less than n over L leaky vertices. Then what you know is that actually random walks from most of the vertices are really badly trapped, right? Because leaky is just reaching L to the 10 vertices, so they're very badly trapped. And essentially, we can prove a much stronger decomposition, where you say, suppose you pick S1 to SK uniformly at random. You can remove epsilon dn edges to get these pieces P1 to PK, just like in the Goldreich-Ron setting. But the pieces now are very small. The pieces actually have size poly L. They're polynomial in L. And random walks from each SI reach every vertex with probability at least 1 over poly L, which means that in effect, if you did random walks from here in the original graph, you can actually effectively find all these pieces directly. And it's essentially, you can use local partitioning to actually find all these pieces by doing random walks in the original graph. And yeah, so you're doing random walks in the original graph, and you can find all of these vertices. And so essentially, if you are in the setting where where very few vertices are leaky, then if G is far from being planar, many of these PIs are far from planar. And you can easily find a superset of PI by just doing poly L walks. And so you can essentially find a superset of this piece and then run an exact planarity algorithm. So just to sort of stitch it together, let me give you the algorithm in total. If there are at least n over L leaky vertices, then you run this algorithm. Pick a random S. You perform you perform some constant number of poly L random walks to get these VIs, and then you perform root n walks from each of these. And if there are less than n, of course, you don't know which case you're in. So the algorithm, the actual tester just runs both of these. But the analysis says if there are greater than n over L leaky vertices, this algorithm works. If there are less than n over L leaky vertices, you pick a random S, you perform a polynomial in L. Remember, L is something like n to the little o of 1, so it's very small. So you perform polynomial in L, L-length random walks from S. You look at all the vertices that are seen, and then you run an exact procedure to find an H minor in S. Note that over here, we have KR. We don't really have H. So in some sense, in this part, the actual minor, the H is not that important. And the H only appears when you use an exact procedure to find the minor in the piece. So at this point, I guess I have about 5 minutes left. Is that correct?
You have more than that. It's only, you have about 15 minutes left.
I have about 15 minutes left. Okay, so then I'll go into some of the technical details. At this point, I'll pause, and if you have any questions, ask me either about the result or the algorithm. So this is essentially the algorithm pretty much in its entirety. Beyond maybe, what actually happens is some of these parameters are chosen. There's some search over these parameters, but that's pretty much it. Okay.
Feel free to.
Hi.
Yeah.
I have a quick question. So at some point earlier, you were talking about there's this magic K number corresponding to P1 up to Pk. Is there an idea how many K is with some simple test?
No. So actually, again, I sort of lied over there that there's actually a K. It's more like, okay, so in this case, sorry, let me go back up. In this case, your K is going to be essentially n over poly L, because each piece is actually really small, right? So it's essentially, it's almost linear, the number of pieces. In general, the way that this is phrased technically is that actually, okay, so I was afraid that this would happen, that I would sort of that I would confuse people with this. So essentially, the way to think of this is that there is a lot of flexibility to pick the SIs. That's really what I meant to say. So once you start with, you can pick a random SI. There exists some piece, and then if you pick a random SI outside this piece, you can also get a piece from there, so on and so forth. So it's some sort of iterative process that actually finds all the PIs in the analysis. There was another question that popped up, but I didn't.
Yeah, the question is that if the goal is to find a H minor, why is outputting a KR minor good?
So you can essentially, as long as R is larger than the number of vertices in H, that gives you an H minor as well, right? So essentially, if you want an H minor, then a minor of a supergraph of H is also a minor. So what we do is we simply set R to be the number of vertices in H, and then run and then do this analysis. Essentially, what it says is if you don't have KR minors, then you're going to have some kind of decomposition where the pieces are of constant, practically of, are polynomial polylog n size. And so then you can just explicitly find these pieces and run an exact algorithm on them. Okay, any other questions? All right, so I will continue. And now I'll sort of try to tell you about some of the technical, some of the tools used to get this result. And my focus is actually going to be on proving that, on this part, if there are at least n over L leaky vertices, then the random walk algorithm finds a minor with high probability. Now, what are the roadblocks in this? So note that L is actually quite small, right? N is like some n to the delta. So there are actually very few leaky vertices. And all we are assuming is that, we're assuming something about what happens with the leaky vertices. The rest of the graph is completely uncharted territory. It's like the Wild West. We have no control about what is going on over there. And it happens to be the vast majority of the graph. So we know that random walks from here are going to end up in the uncharted territory. Now, if you think about it a little bit, because we only have some condition on the vertices here, we only can, the seed vertices need to be in R. Like the VIs that we were using to find the minor need to be in R. Otherwise, there's really no hope of analyzing anything. So let us walk T length random walks. So T is going to be something that depends on L, which I'll show you shortly. Let's walk T length random walks on the SIs to get VIs. So the T length walks, they may go in, they may go out, but we only want to look at the walks that go in because these are the only seeds that we can hope to connect. Now we have two main questions. Why will random walks from these VI VJs connect with each other? Why can we get the birthday paradox style argument to work? And the second problem, which is harder, is how do you control the intersection behavior so you actually get a minor? Because these walks are now going to go into this uncharted territory and they can do anything. And one of the main technical tools to do this is to actually construct something that we call the R returning walks. So this length T that I said is going to be a multiple of 2 times L. And I'll explain why 2 times L shortly. And we're only going to focus on walks that return to R every 2L steps. So in the analysis, we will only look at walks that sort of go out, but they have to come back to the set every 2L steps. So they do this sort of pattern. And we are only going to look for minors formed by R returning walks. And the way I like to describe this is minors must come back home periodically because they're minors. So they have to come back, and we will only look for minors that are formed by this sort of process. Now you might ask, why does returning actually help? So remember that the definition of a leaky vertex is that the length of PVL, the 2 norm squared, is at most L to the minus 10. And PVL is the vector of an L length random walk from V. And we know that that norm is small. Let us look at the probability of a 2L length random walk in the original graph, right? So this random walk may go outside, that goes from U to V, a 2L length walk from U to V. Now, what is this probability? Well, we can look at we can fix the W that is reached after L steps. And we want a walk that goes from U to W, and then from W to V, and then we sum over all V. And that's just this expression that says you sum over all vertices W. You look at the probability that you start from U, do an L step walk, and end at W. That's PUL, that vector, and the Wth coordinate. Then you do an L length walk from W, and you get to V, right? So that's this term here. Now, this is where the fact that it's bounded degree is used, is that technically the random walk that we do is a symmetric random walk. So by symmetry, the probability of starting from W and ending at V is the same as the probability of starting from V and ending at W. So you can switch those. And so you get this is the sum over all W of the probability of going from U to W in L steps and V to W in L steps. But this is just the dot product of these corresponding vectors, right? So you look at essentially the L length random walk from U, the L length random walk from V, and you take the dot product of those vectors. And then you apply Cauchy-Schwarz, and you get that this probability is at most L to the minus 10 for all pairs U and V, right? So this is sort of a very strong property that we get from the leaky property, which is essentially what we exploit. Now, what does this mean? Let's go back and look at a walk that returns once, right? So this is a 2L length walk that starts from some V and returns. Now, because this probability of a 2L length walk from U to V for all UV is at most L to the 10, after one return, the walk actually can end up at any of L to the 10 vertices, at least L to the 10 vertices. So it's sort of spread to L to the 10 vertices after doing a 2L length walk. And if you do 2 returns, then this grows exponentially, that after 2 returns, it is likely to be in any set of size at least L to the 20. So for every return, it starts expanding its position, or where the random walk ends up expands exponentially within the leaky set. This is independent of what happens in the uncharted territory, and this is important. It doesn't matter what this part of the graph actually looks like. And so after each return, the returning walk is spreading exponentially in R. And this is really the property that is exploited quite heavily by our proof. And the problem, of course, as you might say, is but the algorithm doesn't know what R is. It actually cannot perform returning walks. It only performs random walks in the original graph and hopes that these are returning walks. So we have to argue that the probability of a returning walk is sufficiently high. And this is tricky because essentially the probability of a return essentially sort of cuts down the, for every return, the probability of a returning walk is going to go down exponentially. But more returns means more control on the intersections. And the reason for that is this, that for every return, I know that it's expanding out more and more. So the expander analysis tends to work out well. On the other hand, the more returns I force, the less probability that the algorithm that does not know R can actually produce a returning walk. And so there's a delicate dance of parameters over here where you have to choose the number of returns very carefully. Again, all of this is only done in the analysis. The algorithm is simply just performing random walks in the original graph. And in short, these roadblocks of how the VI-VJ pairs connect and how the intersection behavior is controlled is really solved through a detailed analysis of the returning walks. Now, I'm not going to get into more technical detail here because I'd like to talk about some of the open problems that I think that some of these techniques might help in. But I can take more questions on this maybe when I finish. So I'll skip over that. And remember that the algorithm was essentially, there are 2 cases The algorithm doesn't know which cases. The algorithm just runs both of these. But in the analysis, if there are at least n over L leaky vertices, you do the random walk-based algorithm with the birthday paradox. And if there are less than n over L leaky vertices, then essentially you just do a local search. You just pick a random vertex, you perform a bunch of random walks from that vertex, you look at all the vertices that are encountered, and then run an exact, let's say, planarity test on what you saw. Just a few comments on the decomposition statement, which said, that you have the sort of decomposition where each PI is of polynomial in L size and can be found by random walks. This is proven using the Lovász-Simonovic curve technique. It's a lot of sort of spectral graph theory. It's an adaptation of Spielman-Teng's analysis of local partitioning, and it's a little tricky because the partitioning the random walks are on the original graph. Typically, all these partitioning algorithms do it recursively. They find a piece, they remove the piece, and then they find another piece by doing random walks on what results. And so there's some techniques and some care that is required in doing this analysis. But once you put all of these things together, you get the main result. So just to recap, the main result is that there is an O star of root n, basically an O of root n time algorithm that does the following: that if G is epsilon far from being H minor free, then the algorithm actually produces an H minor in G. And I think the most obvious question that sort of comes from this is, can we get a dependence of the form O of D root n, where D is the average degree, not the maximum degree? I believe this should be doable. Of course, we lose a lot of things with the symmetry of the random walk, and so we may have to use, we may have to replace things with the appropriate Laplacian, but this seems like, morally speaking, this should be doable. But I think what I find more compelling is, does this provide a toolkit for using random walks for problems that have minors? And I've not seen too much of this, and this is probably just my ignorance of a lot of graph minor theory literature, but this seems like an alternate algorithmic scheme. So let me discuss 3 concrete problems here, which I think are very interesting. So let's start with the simplest one, which is actually directly property testing. That is there a two-sided tester for planarity that makes poly 1 over epsilon queries? And the current bound by Levy and Ron is quasi-polynomial in 1 over epsilon. And this is considered as a fairly important problem in the context of property testing. I do believe these techniques can be used. And this is something that we're working on. But note that the walks that we performed actually had at least a polynomial in L, in log n. And so getting constant time from there seems tricky. The concrete question number 2, which is I think maybe a question that was asked earlier, is really, does this help in getting better minor finding algorithms, just in the worst case? And I think this is very interesting. So again, deciding if a graph contains an H minor can be done in quadratic time by Kawarabayashi, Kobayashi, and Reed. If the graph has many leaky vertices, then we know that we can do it in root n time. So really what's left is, if the graph has very few leaky vertices, in which case it satisfies these decompositions, does the problem become any easier? I don't think that the current techniques are going to give us anything, because it only helps you find it when there are many leaky vertices. But this might sort of guide us towards the hard part. And I think this is a very, very interesting question. And a third question, which I think would be really nice, is, can this be used to give linear time algorithms for root n size balance separators in H minor free graphs? And I think that there is some notion of, because a lot of spectral graph theory techniques are being used, there may be some, maybe this would give some toolkit for this. There's a long line of results on this, on finding root n size balance separators in H minor free graphs. Effectively, the state of the art is an n to the 1 plus epsilon algorithm, but it has a tower dependence on H. And subsequently, there has been interest in getting better dependence on H, and something that is subquadratic. So I think that some of the random walk techniques may be useful in improving this, in trying to get this bound as well. And sort of with that, and with these pictures, interesting pictures that I spent lots of time drawing, let me end the talk. Thanks a lot.
Thanks, Ash. Do we have any questions?
So yeah, does the algorithm actually use the knowledge of D crucially? It doesn't, but there are places in the analysis where things will start breaking. So for example, if your graph was an apex graph, right? You had a graph and then you had this one vertex connected to everything. The random walks start going and hitting the apex vertex, and that starts screwing up the analysis. So I think that, I think that it should be possible to get a dependence on the average degree by sort of appropriately changing all the spectral graph theory, by maybe replacing every time the random walk, maybe the random walk, we force the random walk matrix to be symmetric, but maybe, even if it's reversible, some of the stuff would go through. So I think that should be doable, but it will require some effort. Yes. Would the algorithm work in the general graph property testing model? Yes, I think so. Actually, even as stated right now, there's not too much that's being used about the degree bound. It's only used really in the analysis, because it's really just performing random walks and doing some local search. So I think that the algorithm will work in the general model. And just to tell the others, the general graph model essentially says that effectively captures what you can do through random walks. I mean, I think that's one way of looking at it. And it allows for vertices to have unbounded degree.
Any other questions?
Hi, this might be an odd question, but I was wondering, earlier you had a result showing that if you control the length of your random walk with a certain bounds, and then you can find cycles. Do you have any statement as if I extend the length of my walk, random walk, I can find cycles of various lengths?
Yeah. So the result by that long list of Chumai, Goldreich, Ron, myself, Shapiro, and Solar does show that if you, it depends on what length you're looking for. If you're looking for any constant length, then that result essentially gives you that proves the bound. Are you looking for even longer cycles? Because for any constant, the problem is done, or maybe even polynomial in n, I think that result solves the problem.
So I guess the question is that, if I imagine a particular graph, that I could have cycles of certain length, and I'm trying to figure out whether there's a limit, right? So right now you're saying that, okay, if I have bounded length of random walk, I can, 2 walks starting from the same node will end at the same node after a certain number, and I'm trying to see what's the limit of this. If I keep walking, is it, do I just count, keep finding larger and larger cycles? Or eventually there's going to be a self-intersection, and that's a limit.
That's a good question. I'm not entirely sure. I mean, so usually the way that the algorithms are stated is that we don't care for the dependence on the actual size of the cycle. We just say that, for any constant, we can get something. And I don't know whether that dependence is really benign, so that if you were to sort of extend that length, what it would behave like. I mean, I'd be worried about instances where, let's say that, your graph was just one big cycle. Then, then there's really nothing interesting that the algorithm does. Maybe I don't think I have anything beyond that to say. By the way, the way that those algorithms work is they basically, they try to sort of, so essentially it reduces the problem of finding, let's say, a cycle of length 4 to a cycle of length 3. And then it reduces the problem of finding a cycle of length 5 to something of length 4. So it is possible that one can sort of just see how far that analysis goes. And just in this case, if you're curious, the dependence on the actual size of the minor, I think it's probably doubly exponential, like in the size of H.
Are there any other questions? Well, if not, then well, let's thank Seshadhri once more. And in a couple of weeks, in 2 weeks from now, Mikhail Kursky will be speaking So join us then. Okay, I'll take this offline now.
Okay. Thank you, everyone. Thanks a lot.
Thanks, Ash.
Thank you. Bye.